Let D be the region bounded by y equals to, let's see, 1 minus 1/2 x, y equals to 1 plus 1/2 x, and the x-axis. Express integral of d of x, y, dA in the form of dx dy and also dy dx with explicit bounds. Think about this question. Here, this dA just means it's a small area element, and this is just a way to talk about this dx dy that we were talking about, right? This thing here can be called as dA because it's d. This means infinitesimal. A is the quantity, so this is a very small area quantity, right? So if you multiply this dA with the height, you get the volume of the column, and you're adding up every column volume over this domain D, so you get the volume under the curve. That's what this means. Okay? And therefore, dA could sometimes be written as dx times dy, or it could also be written as dy times dx. Okay? All right. Okay. And the purpose of this question is to show you that while it is true that you can write such an integral in both dx dy and dy dx, sometimes choosing one over the other is better. It's more convenient. Okay, so let's try to write down what we have. So y equals to 1 minus 1/2 x. So that one has 1 as the y-intercept, and 1 minus 1/2 x, that's a negative slope, just like this. Maybe I did too much, but definitely this is longer than that, right? So enter it twice. I'll do it like this. Okay. So, all right. So what's the x-intercept for this one? 2, right? If you plug in 2, you get 0 for y, so you know that it passes through 2, 0. Okay, what about this one? It has, again, it has 1 as the y-intercept, but it has a positive slope, so it's like this. What's the x-intercept for this one? Negative 2. Okay. And then the x-axis is this one. So do you see the region D? What is the region that's bounded by these 3 lines? It's this triangle. So that's what we are calling D as. Okay. Now let's first try dy dx. So I want to express just like this, x, y. I'm really trying to figure out what goes in here and there. Now having dy inside means what? Which area are you painting this region?
Upwards.
Upwards, because dy is increment in the y direction, so you're trying to paint everything like that. And I guess the place where the paintbrushes start is easy. You're always starting from here, right? So what is this one? What's the equation of this? Y equal to 0. So that's easy. That's easy. And I guess I can even put this in. What's that? Negative 2 to 2. If you actually did the integral and flattened it to make a one-dimensional integral, it's from negative 2 to 2. So the thing that goes in here is negative 2 to 2. What's hard to say is this one, because you actually have two different regions. Right? It's y equals to 1 minus 1/2 x if you're on this side. And this is y equals to 1 plus 1/2 x if you're on this side. Does anyone have a question so far? Okay. So you're trying to express this thing, right? So that's like the best I can do at this point. But then you say, well, why do you have to do everything? Why do you have to describe everything at once? Maybe a better way to describe it is just make it as a sum of two things, this plus that. How's that? Not bad, right? So what you say is, okay, you see, that integral is really, you can think of it as sum of two integrals. We're on the left side, which is from x from negative 2 to 0. When x is from negative 2 to 0, you go from y equal to 0 to where? What goes in here? 1 plus 1/2 x, right? Y equals to 1 plus 1/2 x is this curve right here. That graph. Plus, now for the second part, what should I make x to be? 0 to fx comma y dy dx. And y goes from where to where? 0 to 1 minus 1/2 x. That's it. That's how you express using dy dx.
That's the only way.
Yeah, for dy dx, that's the only way. Okay. So that's the first part. Okay. And now let's try dx dy. How would you express this in terms of dx dy?
So for x.
You're trying to go that way, right? You're trying to paint it going right. And you're right, because you're trying to do that, you have to express where it begins and where it ends as x equal to something. Okay. So we have the task at hand, which is to express 1 plus 1/2 x as x equal to something. You have to solve this for x. So let's try that. How do you do that? Subtract 1, so y minus 1 is 1/2 x. And you multiply by 2, so you get x equal to what? 2y minus 2. So this equation, which we're calling as y equals to 1 plus 1/2 x, has a new name. It's same as x equals to 2y minus 2. Okay? How about this? Well, do the same thing again. Y minus 1 is negative 1/2 x, right? If I move the 1 to the other side. Now multiply by negative 2, what do you get? X equal to negative 2x, and then 2y, sorry, what do you get? Negative 2y plus 2. That's the equation for this other one. Okay. Therefore, the integral of dA, if you express it in terms of dx dy, fxy, it's from where to where? What should I put down here?
2y minus 2.
Where does it end?
Negative 2y plus 2.
And your y value goes from where to where?
0 to 1.
Okay. So you see that if you express the integral using dx dy, you only get a single integral, which presumably should be easier, I think, than trying to deal with two integrals. So this is to demonstrate that, yes, there is a difference between dx dy and dy dx. Sometimes one is more convenient than the other. Not only that, I'm going to show you in the next class integrals where if you try to do it one way, it's impossible. You can only do it the other way. So that's a very interesting example.